where we will start with a new chapter, which is chapter number 6, and where we will look at anorganic nutrients. So it's an important shift now because we have been talking always about macronutrients, so lipids, proteins, carbohydrates, and water. But now we will really move into the micronutrient stories. And although the fact that they are needed in smaller amounts does not mean that they are less important. On the contrary, I would say, because for many of these micronutrients, we either have problems with undernutrition or we have problems with overnutrition. So both of them are actually possible. And we, of course, cannot deal with all the elements that you can find in the table of Mendeleev, but we will deal with the most important ones. And you can see them actually here on the first slide, where we divide them into the so-called main elements, which is hydrogen, oxygen, carbon, and nitrogen. They are present for more than 1% of the total atoms. And this is mainly the case for water, carbohydrates, proteins, and fats. If we go to the minerals, then you see the concentrations between 0.1 and 1% of the total amount of atoms. We have the story of sodium, potassium, and chlorine related to water balance and blood pressure. And we have the story of calcium and phosphate, which is mainly related to the skeleton, and so the osteoporosis effects. There are two extra elements, magnesium and sulfur. We will say a few small words about it. I would not consider them as important as the previous ones, but they do deserve some attention, especially sulfur, for which today we do not have any clear recommendations. For magnesium we have, but I consider for the moment sulfur a little bit more important than magnesium. And then the second layer, but that's for next week, is the trace elements. So you even go lower than the minerals, less than 0.1% of the total amount of atoms. We're mainly talking about iron, zinc, and copper, which are all related and discussed together in metabolism. We have iodine and we have selenium. And the most important physiological effects are anemia, so low amount of red blood cells, and endemic crop, which is actually goiter, and which mainly occurs with low or high amounts of iodine. On the second layer, you see chromium, molybdenum, manganese, fluor, and cobalt. They are second-order trace elements. They can cause some problems, but usually not for the whole population, but for very specific target groups. So we will come back to that later. So general principles in terms of the mineral balances, mostly the alkali metals, like for example, potassium and sodium, and also chlorine, can be completely filtered by the glomerulus. So there is no selective filtration. They just follow the path of the water, which is quite easy to do. We mostly have problems with sodium. So one of the ways to correct for that is to consume more potassium, because potassium and sodium in metabolism are more or less keeping each other in balance. So the higher you take in the potassium, the more it can have an effect on the sodium balance. And potassium is mainly found in vegetable foods. And potatoes, for example, is a very rich source of potassium. And in some cases, it's one of the most richest sources that we have, especially in the westernized diets. Trace elements are, generally speaking, not so well available. So if you go for vegetable foods, you have a low bioavailability of trace elements, but you do have a quite higher intake of potassium, which is beneficial. For meat, as an example for the animal-based products, we can see an increase in the levels of sodium, especially for processed meats. And we also have a rich product for trace elements. Iron, copper, zinc, all these ones are physically present in meat, and they are also well available, much better than, for example, in vegetable type foods. Meat, however, does not contain a lot of calcium. So the calcium phosphate ratios are quite low, and usually the balance between the two cannot really be equilibrated or influenced in a positive way by the use of animal-based products, in this case meat. If we look to dairy foods, then we know that calcium is important. I think that's known by everybody. You will see later that what is mostly important for us is the proportion between calcium and phosphate. Because if you take in cow's milk, then the proportion between calcium and phosphate is quite low. I would say it would be lower than 1.4 because there's quite a lot of phosphate present in cow's milk. And if you have well operational kidneys, which is the case for an adult person, this is not really a problem because you could quite easily drink cow's milk and the kidneys will correct for the right calcium phosphate ratio. However, if you're a sensitive person where the kidneys are not functioning, and like kidney diseases, or for very young children, like infants, where the kidneys are not yet developed, in those situations, the calcium phosphate ratio is important. So in that case, the only way you can do is either take breast milk or you take cow's milk derived infant foods. So foods that are modified in such a way that the calcium phosphate ratio exactly fits the calcium phosphate ratio of breast milk. If you don't do that, pure cow's milk cannot be given to a young child because the calcium phosphate ratio is not optimized and the kidneys of the young child cannot handle this. Generally speaking, if you're adult and everything is fully grown, then you also have a very strong regulation of the uptake as well as of the excretion. So the balance as such is quite tightly regulated. In Belgium, we have a problem with sodium intake. I think if you remember your own exercise, you might be able to understand whether you had a problem yourself or not with the intake of salt. So in Belgium in 2009, I think about 14 years ago, the government decided to do something about it. And so they asked that all the people from, let's say, the food producing sectors, so the ones that are bringing foods on the market, were asked to come together and to discuss about how sodium in foods could be reduced for humans. And so we made an exercise. I also participated in that time in that discussions. So we came up with an exercise in which we saw which fraction of salt is taken away from all the different food fractions. So we came to some very interesting and surprising results. So the first thing is the bread and the bread product group, which is very important in Belgium because we consume quite a lot of bread. You can see that this fraction will correspond to almost 25% of the daily sodium intake. It's coming from bread and bread products. The reason why sodium is there is mainly because of taste. If you would remove the salt, you know that you have tasteless bread. So people don't like that. That's why salt is actually added here. Technologically speaking, it is not difficult to remove the salt. The product will stay stable. The only thing you lose is a little bit of the sensorial properties, which could be an issue, but technically speaking, the product is safe for consumption. Second group is the meat and the meat product group, especially the processed meats. So the salamis and the sausages and things like that are quite enriched in sodium, giving us about 12% of the daily sodium intake. And the third one was soups. And we mean especially the prepared dried soups that you can buy in the supermarket. You put them in water, you boil it, and then you consume it. So these types of soups, generally speaking, are, and especially in the past, were quite rich in sodium and salt. All the other ones are a little bit less. So based on this graph, we finally came to the conclusion that 3 sectors should at least do more proportional exercises or efforts in order to try and reduce sodium and salt in their products. The first one was bread and bread products. The second ones were the soups, of course. And for the meat sector, it was a little bit a delicate discussion because if you would remove the salt, you might also induce unsafety of the product, and not only sensorial properties, but also microbial outgrowth, to some extent, color formation could to some extent be related to the salts that they're using in the processed foods. So it was much more difficult there to do that. So the government decided that new research projects were set up, and that was done more than 10 years ago, in collaboration with the industry, in order to find ways to reduce salt in processed meat products. And today, I think they have already quite some alternatives which are now used in meat and meat products. The total salt intake measured by a questionnaire was 7 grams per person per day. And remember, the recommended amount for salt is around 5 grams per person per day. Yeah, so we're talking about higher levels on average for the population compared to what is required. However, if we would measure it in the urine, which is a completely different marker than when you would measure it with questionnaires, the average intake level in 2009 was 11 grams per person per day. So you see the difference between the two. Questionnaire 7 grams, urine 11 grams. It's very clear that the type of biomarker you use to measure the intake highly determines the outcome of the results. Probably with the questionnaires, people do not always explain well what they eat, meaning that you give an underestimation of the real salt intake in humans, which is probably even a little bit higher than the 7 grams per person per day. In the meantime, we are now 10 years further. All these activities and actions have already been taken, so we see a gradual reduction in salt levels in foods as well as in the urine. But I must say that we're still not there, and so we are still above the recommendation, but gradually but slowly salt intakes are being reduced. So why is sodium so important? Because we are mainly talking about sodium. Potassium has benefits, sodium has disadvantages. So it's important to try and understand a little bit how that comes. Sodium is found in the skeleton. It is important for the sodium-potassium ATPase activities, which you already know, for the absorption of amino acids and glucose, for the transfer of nerve tissues, pulses. So sodium must be there. So you cannot imagine a situation where you are in hyponatramia, which means too low concentrations of sodium in the blood. We don't want that either. But it's very clear that in most cases, there is just too much, probably because of a very tight and difficult regulation of sodium. The absorption takes place usually by active transport. Chlorine just follows in passive diffusion because of the charge difference. And then there are specific osmotic transport systems for water. And so this is the way by which water is absorbed. First sodium, then chlorine, and then by osmosis, water. In the case of cystic fibrosis, the first one which is absorbed is chlorine, and then sodium follows. So it's just the other way around. So first chlorine absorption, then sodium absorption, and finally the absorption of water, which happens in the lung tissues. And when there is a defect in the chlorine transporter, then you get cystic fibrosis, which is also called mucoviscidosis. It means that you have a layer of mucus which deposits, for example, in the respiratory tract. And yeah, you get all types of infections. You have to take strong antibiotics. So these people usually, don't have a very long life expectancy. And so 18 years, 20 years is a general average. It's a quite serious disease still today. Then in terms of excretion, we see that excretion can be done by the urine, by gastric juice for chlorine, by the sweat for sodium, and also by the skeleton. And you can also control sodium intake. In case you have low levels of sodium, the sodium can be absorbed from the GI tract. This is done by the release of renin, a hormone which is released from the kidneys when the levels of sodium are quite low. So you have a low blood pressure, for example. Renin is released. Renin will lead to the release of angiotensin. This angiotensin will interact with the jejunum and the ileum, which means that you will get more absorption of sodium. Angiotensin 2 can also interact with the kidneys and can lead to the release of aldosterone, a steroid hormone, which goes to the colon and which also leads to more absorption of sodium. So the blood pressure can quite quickly lead to more uptake of sodium in the GI tract, thanks to the combination, in this case, of hormones that are produced by the kidneys. At the same time, when the plasma sodium levels are low, you get the release of renin by the kidneys. You can also have the conversion of angiotensinogen to angiotensin 1, which is done in the liver. And then you get a hormone, an enzyme, which is called the ACE enzyme, angiotensin converting enzyme, which converts angiotensin 1 into angiotensin 2. And this angiotensin 2 is a strong vasoconstrictor. It interacts with the adrenal gland, releases aldosterone, and aldosterone will lead to less excretion of sodium by the urine. So when you're low in blood pressure, low in plasma sodium, you get more absorption of sodium by the GI tract and less loss of sodium by the urine. And in case the blood pressure is high, the mechanism is just reversed. So all the hormones are gone, no absorption in the GI tract, and more release of sodium in the urine. That's how the system is regulated. So you can measure then the recommendations, which are based on sodium balances, measuring the amounts in feces, sweat. 2 grams per day is the average requirements for sodium today. And you can see that if you are losing a lot of sodium during extreme exercises, you get in a situation of hyponatremia. And so too low concentrations of sodium inside the blood, which could be a problem. So in that case, you have to see that enough sodium is coming in again, which, for example, can be done by the use of specific foods or drinks that are produced for athletes and sporters. We know now that salt uptake is related to hypertension. So people that are moving, for example, from a country with low salt intakes to a country with high salt intakes will also see that the hypertension goes up. These studies are known. So hypertension to some extent is linked to salt intake. However, the reverse is not necessarily true. If you go from a country with high salt intake to a country with low salt intake, this doesn't necessarily mean that you also have a reduction in sodium and in blood pressure. And so it's a little bit a difficult situation, which is highly determined by the uptake of sodium, especially from low to high, but not from high to low. Potassium is a little bit more interesting for us. It has a higher diameter. It is a little bit less efficient to absorb and retain it in the body. And one of the strategies you can follow to reduce sodium content in foods is by replacing sodium by potassium. The food industry is already working with that. So sodium chloride becomes potassium chloride, but you cannot have it in excess. So just the same as with sodium, if you would take it in too high levels, it could also lead to negative effects. For example, on cardiovascular effects, heart rhythms could also be influenced by too high extreme chronological intake of potassium. For chlorine, the recommendations are here, mainly in gastric juice, and we also recover most of it by reabsorption in the GI tract. I ask you to think a little bit why sodium is more critical than potassium. These elements are quite closely together. They work always together. But in terms of blood pressure, the major target is sodium. Why is that? and think a little bit about the location of sodium and potassium in the human body. I think we explained that enough in the other chapters. So think carefully, where is sodium and potassium located? And based on their position, you can quite easily predict which ones will mainly influence blood pressure and why. So this brings me to an important trial, which is called the DASH sodium trial. You can find the article on Euphora under the map of references. And it's a really interesting trial. It's a very powerful one that also shows very clear results. It's a clinical trial which was done in the US, whereby people were only allowed to follow the instructions of the researchers. So nothing was done outside the study. The whole life was actually focused on this study, and which is, of course, a whole included and a very, let's say, powerful study design. What did we do? You go on the x-axis, and on the x-axis, you have 3 levels of intake: the high intake, the intermediate intake, and the low intake. The high intake is the intake levels for sodium we have today, so highly above the recommendation. The intermediate intake is the intake which is linked to the current dietary recommendations, which is, for example, 2 grams per day. And the low intakes is the intake which is below 2 grams per day. In principle, that is not necessary, but they also study this in this trial. On the y-axis, the top figure, you can find the systolic blood pressure, so the upper blood pressure, and the lower figure gives you the diastolic blood pressure, the lower pressure. So we move from left to right, which means that you move from high intakes to low intakes. And the intakes are completely regulated by the sodium, which is present in the food. So in other words, going from left to right is actually pushing the industry who brings products on the market to reduce the salt content in their foods. You can think, is this a push strategy or a pull strategy? We saw that in the first lecture of the course notes. You can think about it. In this case, you're only going to work with the producers, not with the consumers, and you're going to force them to reduce the levels of sodium in the product. Yeah, in this case, you go from left to right. And if we do that, you can see very clearly that all curvatures are going down in blood pressure. The upper blood pressure as well as the lower one. And the study was very powerful because, for example, they created supermarkets whereby the foods were all reduced in sodium, compared to another supermarket where the same food could be bought, but where the sodium level was not reduced. So in this way, you can see that there's a very powerful case control. You can really look at no intervention versus intervention. And when you do that and you control it, and people will only eat the foods that are given by the researchers, then you see that the blood pressure is significantly reduced in both cases. So that's the lines from left to right. The second lines are from top to bottom, so the vertical ones. In those situations, 2 different diets were used. The first diet is called a control diet, which is the average American diet, which was consumed there. The second one is the so-called DASH diet. And DASH stands for Diet Approach to Stop Hypertension. And in this case, you eat more vegetables and fruits, you eat a little bit less fat, a little bit less processed foods. So you bring it back into equilibrium, into the normal healthy triangle structure that we know. So in this case, you're going to work together with the consumer. You're not going to work with the producer because you do that at the 3 levels. So the high intake, the medium intake, and the low intake. And you don't change anything to the products that are on the market. Also with this, so with the DASH trial, you can see that if you change the dietary patterns, both for the systolic blood pressure as well as for the diastolic blood pressure, you see that they go down. Yeah, so it's very clear that also the second principle, and you can think whether it is a push or a pull strategy, the second one, but it's again clear that in this situation, working with the consumers can also lead to reduction of blood pressure. And so the ideal case that they came up with is the combination of the two. Because if, of course, you move from left to right and you go from top to bottom, then you reach the lowest blood pressures. And this, in practice, will be that you will apply a push and a pull strategy. You will work with the producers and hope that they gradually modify the foods, perhaps not drastically, but gradually. And secondly, you work together with the consumers, and you also hope that the consumers are willing to slightly adapt the diets. They don't have to adapt it completely, but if they have a small, slight adaptation, and also the producers have a slight adaptation, the combination of the two will be strong enough to reduce blood pressure in humans. So I hope this gives you a very clear idea on how an ideal design is set, and especially how powerful it can be in terms of clinical outcome. If we look to the biomarkers, then you can see that the study was well designed, because here is the high intake, the average intake, the low intake for sodium. Here is the DASH group and the control groups. And there you can see that the sodium in the urine is gradually reducing if you go from high to low sodium intake, while the potassium is already changing between DASH and control. And for the rest stays constant, because the potassium effect is, of course, linked to the diet effect, the fact that the diets composition are shifted. So that's for sodium. I hope this is more or less clear for you, so that you also understand what is the problem, that you also have an idea which interventions could work, and that you can see that push and pulls together or single could have a very clear influence on regulation of blood pressure in humans. So now we switch to calcium. Calcium is a second example of a mineral. It's not the same as sodium or potassium because it's double charged, and a double charged element can quite easily bind to protein. So it means that it is not very well filtratable in the kidneys. Part of the calcium will just pass by and will not go to the urine. And so it can go, but then it has to be liberated from the protein before it can be filtrated. Calcium is important for osteoporosis, which means types of bone diseases, which is nicely illustrated with this figure. So on the x-axis, you can see the age of persons. On the y-axis, you can see the bone mass. And you can see that a person, when they are young, so younger than 20 years old, you see that they are growing. And as a function of time, the bone mass is increasing in density. You'll reach a maximum, which will happen around the age of 30 years old. So most of the students younger than 30 are still in a growing phase for the skeleton. At the age of 30, more or less, your maximum is reached, which we call the peak bone mass. And the 1 and the 2 is the males versus the females. So you can already see that the males have a slight advantage compared to the females, because the peak bone mass of the males is higher than the females. Once you reach the maximum, the only thing you can do as a function of time is try to keep it as maximum as possible, because you cannot go further, you cannot further increase the density. It can only go down, but you can try to postpone it as long as you can. And you can see here for the first person here, number 1, it stays steady quite long until 55 years of age and 60, and then you can see that it gradually reduces for males. In case of females, the same thing, so you can try to keep it as long as possible in a horizontal state, but then, especially around 50 and 60, which is more or less the menopause for women, and you have hormonal distributions and changes, which can also lead to solubilization of the skeleton, and which you can also see that you can have a rapid or a more rapid reduction of the bone density, until you reach the so-called fracture threshold. And if you cross that, then of course you get instability in the bone structure, which can even break quite easily. And this is then the issue of osteoporosis. Sometimes it is accelerated. And some people that receive hormone therapies, if there are some genetic deficiencies, you can see it can even go much faster. But in normal conditions, males are a little bit better protected. I don't say they are protected, but it's a little bit better. And females are a little bit more sensitive. We also know that there is an ethnical parameter involved, whereby Caucasian women of the age of 50 and older are a little bit more sensitive than other women around the world. I will come back to that with some potential hypotheses. So it's very important to understand that if you're young and you're still growing, you need to do everything that is possible to get the peak bone mass as high as you can. Yeah, if you stop drinking, let's say, calcium-rich products, if you don't have any physical activity, it could be that, let's say, the peak bone mass is lower, and this also means that you will reach the threshold much faster. So keep it as high as you can. This is one of the strategies to avoid osteoporosis. Here you can see the start of an osteoporosis, which takes place in the spine column in the back. You can see that the structure becomes less dense, more solubilization of bone mineral, which in this case is still acceptable because you see that the connections are still there. So the stability of the spine is still more or less stabilized. But in a worst case situation of severe osteoporosis, you can see that all the internal parts are solubilized. There is no, let's say, stabilization anymore of the internal structure. And then the full weight of a person who is 60, 70 kilograms, which is normally carried by the spine column, will not be able to be maintained anymore. And it's too high weight, and the spine column will actually collapse. And you can see that here on the northern part and the southern part, just collapsing of the spine column, and all these individual parts of the spine column come together, they touch each other, there are nerve tissues there, and this is extremely painful. And so these people also bend forward. It's very difficult to walk, it's difficult to sit, and this is a severe form of osteoporosis, which is not easy to correct anymore. And so it's better to prevent it than to cure it afterwards. If we try to understand the mechanism, then you have to know that we have about 1.3 kilograms of calcium and 690 grams of potassium in the bone skeleton, and the ratio of calcium and potassium is 2.2 out of 1. Now, this is the ratio that you can exactly find back in breast milk. So a young child, where the kidneys are not functioning well, you can actually give them breast milk because the calcium phosphate ratio is more or less stabilized. It's exactly the same as the bone skeleton. So you will not run into problems in this case with regulating proportion calcium phosphate. However, if you would take cow's milk, then the proportion is 1.4. So much more phosphate, much less calcium. And if the kidneys are not operational, then of course you cannot regulate it anymore. And then you get too much phosphate and too low amounts of calcium. And we call that hyperphosphatemia and hypocalcemia. That's too low levels of calcium, too high levels of phosphate in the blood. So you cannot do that, and that's why infant foods need to be adapted in calcium phosphate ratio. The skeleton contains collagen with chondroitin and apatite. Apatite is a mineral composed of calcium phosphate, fluor, chlorine, and sodium. And there is a fixed proportion between calcium and phosphate, which is 2.2 out of 1. Inside the skeleton, there are two cells, the osteoblasts and the osteoclasts. A blast is an incorporating cell, a clast is a mobilizing cell. So you can already imagine that when you are young, Then the osteoblast is very active, so you get more incorporation of calcium. When you're older, you get more osteoclast activity. So after a while, the bone skeleton is broken down because the mobilizing cells become more active than the incorporating cells. So the research on osteoporosis is, for example, trying to influence the activity of osteoblasts and osteoclasts, and doing this in such a way that the bone skeleton remains stable. Calcium also plays a role in enzyme activities, and also phosphate plays a role in buffer activities and ATPs and things like that. So although calcium and phosphate are mainly associated with the skeleton, you must take into account that there are some other quite important regulating mechanisms too that are not directly linked to the skeleton as such. So if we look a little bit to the roles of calcium in the human body, then they're quite important for intracellular signaling. So sending messages out between the cells, communicating between the cells and in the cells. This is something that is mainly linked to calcium. And in your biochemistry, you probably learned that if you have a hormone, like insulin, it can touch the outside membrane of the cell, for example, the pancreas cell, or other types of, or general cell in the body to absorb sugars. Then inside the membranes, there's a phospholipase C, which is activated. You break down the phospholipids into diacylglycerols and inositol triphosphates. This leads to more release of intracellular calcium, and this will lead to more communication with the nucleus of the cell. And so you get a protein kinase C transcription factor, which is activated, and this will influence cell functionality. And for example, apoptosis, or programmed cell death, or cell growth, or whatever. So the basic idea is the hormone stays in solution outside the cell, interacts with the membrane, and the communication with the nucleus is done by the use of calcium. So you can now understand that the body does not like high fluctuations in calcium levels. The calcium levels in the blood are always very stabilized. Otherwise, you get problems with signaling and messaging. So you have to keep it as constant as possible. And this constant supply is actually done by the regulation of the plasma calcium. And so you see that here in the middle, you see the data, it's very, very small fluctuation. In principle, the calcium levels in the blood are no measure for the calcium status in humans. And it's not possible. Calcemia is not a measure for calcium status of humans because it's very, very constant. And it is actually stabilized by 3 organs, by the intestine, by the kidneys, and by the bone skeleton. So it means that if calcium levels would drop, then all the calcium is released from the other organs. So more calcium from the bones, less calcium released from the kidneys, more calcium uptake from the intestine. And if the levels are too high, then you absorb more in the skeleton, less absorption, and more release by the kidneys. So in this way, you can actually perfectly keep the levels of calcium in the blood stabilized. And this is done by a hormonal system that controls the whole system, and it is also influenced, we will come back to that in the last chapter, by vitamin D. And so vitamin D, you know that, is activated by sunlight. It's also activated in the kidneys, producing a compound that can lead to the absorption of calcium in the intestine. And so if you don't have enough vitamin D in the body, you might get in troubles with the absorption of calcium at the level of the small intestine. So please remember, calcemia is not a measure for the calcium status in humans. The absorption is mainly done in the intestine, jejunum, ileum, and colon. It can be done by active transport, which is mainly done with vitamin D. I just explained that to you. Vitamin D will produce a protein which is called calbindine, and this is the transporting protein for calcium in the intestine. So vitamin D is the responsible cofactor for the synthesis of calbindine. This happens mainly for low calcium uptakes. So people that are not exaggerating in calcium will mainly have this absorption mechanism. And we know that elderly who are usually not too much outside, they're not in contact with sunlight, they have problems with vitamin D, they are the ones that also have problems with the synthesis of calbindine. So it means that they can have problems, disturbances in the absorption of calcium in the intestine. And then the second option is paracellular, between the cells, and that is a diffusion process which mainly takes place at high calcium intakes. For example, the ones that take calcium tablets, for example, you would have more calcium uptake just by classical diffusion. Then in that case, vitamin D is not needed. You can influence it by calcium salts and gastric juice. So if you acidify it, the bioavailability is increased. If it's more alkaline, then of course the uptake is more or less disturbed. For potassium, same discussion. Vitamin D dependent transport, passive diffusion, also depending on the dose that you give, and better absorbed in organic than in anorganic form. You could ask a very simple question, and this is also linked a little bit to your individual task that I'm now correcting. You might think that calcium is mainly coming from dairy foods, for example, cheese or milk or whatever. But some of you did not really realize that calcium can also come from water, classical water. And here you can find a study that was actually measuring the difference of calcium uptake coming from water or coming from dairy foods. The study was done with young women. The study was done by using fractional calcium absorption techniques, which is actually stable isotopes like calcium 44 and calcium 42. So the calcium 44 is going to the food. The calcium 42 is going to the blood. And the difference between the two is the absorption. Yeah, because that's the only difference. The food still has to be absorbed and then comes into the blood. And intravenously, you come directly into the blood. And you measure the two isotopes in the urine. And this is a measure for the absorption of calcium. We call that the true fractional calcium absorption. And they studied different types of products, including waters, and very surprising, the calcium absorption is not significantly different between mineral waters and dairy products. It's about 37%, so 1/3 of the calcium taken in from the food, whether it is water or whether it is dairy products, is not a big difference, is actually absorbed physiologically inside the human body. And you could influence it a little bit, especially for water consumption, by also the intake of solid foods, because then you delay the process and then you increase the chances that calcium can also be additionally absorbed. So please remember, water, tap water, for example, could be a source of calcium for the human body in addition to classical foods. The regulation, I already explained it to you. For example, there's low levels of calcium in the blood. Then you get release of calcium from the skeleton, no release of calcium in the urine, and more uptake of calcium from the intestine. But of course, since the skeleton is a mineral, next to the calcium also phosphate will be released. So the kidneys have to release phosphate extra from the urine. That's why the kidneys need to be operational. If they don't work, then you get these problems both with calcium as well as with phosphate. Calcium shortage is regulated by parathyroid hormone, so a hormone that is linked to the thyroid gland in humans. If there's an overload, you just get the reverse, decrease of the parathyroid hormone, no uptake from the intestine, no losses of phosphate, but more losses of calcium, more uptake of calcium as well as phosphate in the skeleton, which means that you have to lose less phosphate in the urine to compensate for that. And then the recommendations, you already know them from the practicals. You could have more calcium loss in case you eat a high number of protein. because you then have the, let's say, losses of calcium sulfate. Very efficient regulation, so calcium-E is no measure for calcium uptake and status. This is more or less what we accept. And infants can have a problem with hyperphosphatemia and hypocalcemia because the kidneys are not functional. Gallstone formation is the result of calcium oxalate. So too much calcium can lead to bile stone formation. And treatment of osteoporosis is difficult. You probably need to have combination therapies, physical exercises, hormone therapies, specific tablets. So there are opportunities, but it's not easy. Prevention is better than curing here. I told you that there's a strong effect from ethnical background. So it seems that, for example, women living in Africa seem to be more resistant towards osteoporosis than Caucasian women and Asian women living more northern. Here you can see a potential reason for that. So here is calcium intake. This is calcium retention on the y-axis. So you can see that if we start with a high intake and you would reduce the intake, at a certain level there is a cutoff point. So a point whereby calcium is not retained in the body and you get solubilization of the skeleton. It seems that this cutoff point is more sensitive for Caucasians and East Asians compared to African women. And so there, the resistance is a little bit higher, meaning that these persons are a little bit more resistant towards osteoporosis. And this is the same here on the left side. So bone accumulation is actually induced if you go beyond the threshold value. The second potential reason has to do with acidification. If you acidify the body, you can acidify and solubilize skeleton. Acidification might be done in the blood, could be related to some foods. There are acidifying foods, and we can already see that if the pH drops from 7.4 to 6.8, which is a minor drop in blood pH, you can already see that the osteoclast activity is enormously increased with a factor 5 to 6. So the osteoclasts will release much more calcium in the medium just by slightly changing the pH. So it has already a drastic effect. So coming to another problem-based learning question, you might think about it. What could be the effect of bone metabolism in case growing children who are very sensitive for building up the skeleton start to consume high amounts of phosphor? For example, soft drinks like Coca-Cola in place of drinking milk or taking dairy products. So what do you think? Which mechanisms are going to play here that could potentially lead to softening and even loss of bone tissue at a later age? The study that actually is related to that, you can look at it on the website in case you want to know the details, is the Framingham study. A study which takes place every 4 years with the same persons as a function of time. They do some dietary intake studies. They also do measurements on the physiology, including the bone mass density, which is done by X-ray diffractiometry, so DEXA scans, things like that. So you can actually measure the density of the skeleton, and you can see here when the consumption of soft drinks increases, which are very rich in phosphate, that there is also a clear, significant reduction in some of the bone skeleton structures. I must say it is in this case the femur, which is actually the upper part of the leg, which is actually measured. And there you can see that the density is reduced at long, let's say, ages. So you have to see that as a function of time when people are getting older. But there seems to be a correlation, and it is mainly related to differences in calcium phosphate ratios in the foods or the drinks. Where it can go much faster, because of course, if you take a free living person on Earth, it will take several years before it develops. But if you look to astronauts, for example, it can go much quicker. And there's a study that I put online, which is the Gable study of 2022. It's a study which was done on astronauts going into space and who are not really using the skeleton. And you know, you go outside in space, there's no gravity. At that moment, if you stay long times in space, it could be that the skeleton is solubilized because you're not using it and there's no gravity. Well, here they have measured all characteristics of the skeleton after coming back to Earth. So you have the pre-flights, then during the flights, and then when coming back and looking what happens as a function of time. Some people are not sensitive. These are the black lines, and the dotted lines are the ones that are sensitive. So you can see very clearly that once they are in space, as a function of time, all the bone markers are clearly reduced. And so in this case, they worked with the tibia, which is the lower part of the legs. So you see very clearly reductions over the whole face in different parameters. You can restore this a bit when you're coming back on Earth because you're using them again. But for the sensitive people, you can see here that the difference can be maintained for some parameters, not all, but for some parameters it is maintained. You could lose up to 10%. And so it's very clear you need to use your skeleton. If not, it's broken down. And you see that on television, if these astronauts are now into space, they continuously have to cycle on a bicycle in order to keep the skeleton active and to avoid accelerated osteoporosis. The other parts are a little bit less, so I'm going a bit faster. So magnesium is commercialized. Some people say it would be beneficial because it produces ATP. I'm not so sure whether it will improve, let's say, your performance. There has been some link with hyperventilation, which means that people, for example, are stressed or tired, they are frightened. In those cases, you will have a fast respiration with more oxygen and less CO2 in the blood. The pH of the blood is changing, calcium levels in the blood will drop, and then you get shortness of breath, and you get more or less pains that can develop in the muscles. And this means that you get stress again, and because it's a circle in this case. So one of the options is to see that you are resting, that you start respiring in a controlled way. And the third option is by taking magnesium, because magnesium will come in competition with calcium and will maintain the calcium levels in the blood and will, in this case, interrupt the cycle. But I'm not 100% sure if all these things are scientifically well proven. Sulfur, on the contrary, is much more important. It has no recommendation, but it is important because sulfur in amino acids and in proteins means that this amino acid and protein has to be secreted. So it means that all the mucins that are physically present in the GI tract contain sulfur, because mucins are excreted from the wall of the intestine. And it is actually incorporated by the use of an activated molecule, which we call PAPs. And it plays a role, finally, in detoxification. So it could be for mucin production, which is protection, and it also plays a role in detoxification, mainly by the production of so-called glutathiones. It's a small peptide which contains cysteine, and cysteine contains sulfhydryl groups, which is actually sulfate. And on the next final slide, you can see more or less what it does. So here is glutathione in the reduced form. It can actually be converted into the oxidized form, which is called GSSG. In this way, you can actually catalyze a whole set of reactions that are neutralizing radicals. So all radicals, which may be dangerous for you, would all be inactivated by the use of glutathione. So in this way, sulfur metabolism is an antioxidant metabolism and is important for protection of the human body. You can regenerate the original molecule by reducing it again in the presence of a reductase, which is an enzymatic approach which will not generate new radicals. Yeah, so in this way, glutathione is the perfect catcher of radicals and the perfect protector against radicals in the human body. The second function, amino acid transport, is less important. It is there, but I don't think it has major problems. And finally, you can also inactivate toxic molecules by conjugation reactions. And so the glutathione will connect with the toxic molecules, will inactivate them, and then they are water soluble and they are easily excreted by the body. Okay, I think with this, I gave all my slides. It has been a long day. I hope everything was clear for you. I will stop here the recording